Lesson 15, Mean. The mean, or more precisely, the arithmetic mean, is a measure of central tendency, or average, of the data. The mean measures central tendency by finding the center of gravity, or balancing point, of the data. To illustrate this idea, imagine all the data values on a number line. The mean is that precise point for which all the data values balance out. The mean is calculated by summing all of the data values and dividing that sum by the total number of data values. The population mean is given by the formula mu sub x is equal to the sum of all the population values divided by the population size, capital N. The sample mean is given by the formula x bar is equal to the sum of all the sample data values divided by the sample size, lowercase n. The population mean is denoted by the Greek letter mu. Subscripts provide clarification. Here, it's denoted as mu sub capital X, denoting that this is the mean for the population of all the data values. But if the data was grade point averages, we could denote it as mu sub GPA for the population mean of all grade point averages. The sample mean of the data values x is denoted by the symbol x bar. Both the population mean mu and the sample mean x bar are calculated in the very same way. That is, you have to sum up all the data values and divide by the total number of data values that were added. The only difference is the context. That is, are the data values that we're summing up all the data values in the entire population? If so, then we're calculating the population mean. But if the data values are only part of the population, that is, a sample, then we're calculating the sample mean. This notation here, using the summation notation in mathematics, denotes the summation of all the population values. And this sum is divided by the population size, capital N, to calculate the population mean, mu. Here, the same summation notation is used to denote the summation of all the sample values, and this sum is divided by the sample size, lowercase n, to calculate the sample mean, x bar. The following formulas are programmed into the TI-84 calculator. Hence, in this course, the TI-84 calculator will be used to calculate the mean. For instance, calculate the mean exam score for a student that receives scores of 4, 2, 5, 3, 0, and 4 for the 6 problems on their Unit 1 examination and interpret the result. So first we need to calculate the mean for these 6 exam scores. To do that, we'll use the TI-84 calculator. But first we need to enter these data values into the calculator. To enter data into a list, you press Stat and Enter to enter the data editor. You could choose any list to put your data in. If there's already data in a particular list, like there is here in List 1, you can use your arrow buttons to navigate up to the list name you want to use, in this case L1, and then pressing Clear, Enter, will clear out any old data to make room for new data. Now we could enter in this student's Unit 1 examination scores, starting with the first score of 4. And to enter it into the calculator, press Enter. The second score was a 2. Enter. Third score was a 5. And Enter. And then a 3. Enter. 0. Enter. 4. Enter. Now with all the examination scores entered into List 1, we could calculate the mean exam score by pressing Stat, arrow over once to the right to highlight the Calculate menu, and then press Enter to select the 1-bar stats command. Then you have to tell the calculator which list you want it to calculate the 1-bar stats for. Since we put the exam scores into List 1, we indicate List 1 by pressing second and the number 1. That's the shortcut to L1, or list 1. Press enter. The calculator has calculated all kinds of statistics for us, including the mean. So we could read off the calculator screen the value of the sample mean x bar. In this case, x bar equals 3. Now, the population mean, mu, is not displayed on the calculator screen. That's because the result for calculating a population mean and a sample mean give you the exact same result. The only difference is the context in which the data has been collected. That is, was the data the result of a census that is collecting data from the entire population? If so, we would have the population mean, mu. If this data was just collected from part of the population, that is in a sample, then we have the sample mean, x bar. In this problem, we're looking at one single student's score on this one examination, and we have their scores for all 6 problems. So essentially we have the whole population of scores for this student's Unit 1 exam. So instead we should denote this as mu sub x equals 3, denoting that this is the population of all test scores for this student. Now that we've calculated the mean for this data, we then need to interpret the result. Interpretation is different from a description. Descriptions just merely report the results that can be directly derived from the data. For instance, the description of this result could be that the mean Unit 1 examination score for this student is 3. An interpretation gives meaning to this result. That is, it tries to explain what this result is telling us. So since the mean is calculating the center of gravity or the balancing point for the data, the interpretation must give this meaning. So here, the balancing point of this student's Unit 1 examination scores is 3, would be the interpretation. Now to illustrate this idea, we could take all the Unit 1 examination scores that the student had and put them on a number line. Now the mean is that precise point at which all the data balances. Now the mean finds the balancing point or center of gravity by balancing out all the deviations that the data values are from this mean. So, for instance, the score of 3 that the student earned on one of their problems is precisely at the mean. So the data score of 3 is 0 points away from the mean, because 3 actually equals the mean. But the 2 scores on the problems where the student scored a 4 are each 1 point above the mean score of 3. The problem where the student scored a 2 deviates 1 point below the mean of 3. The score of 5 deviates 2 points above the mean. And the score on the test where the student earned a 0, 0 is 3 points below the mean. So here what the mean does is find the point where all these deviations of the data values from the mean balance out. If you look at the deviations below the mean, we have -1, -3, or a total of -4 points below the mean. And if we look at the deviations of the scores above the mean, we have +1, +1, and +2, which gives +4 points above the mean. Now the -4 points below the mean and the +4 points above the mean cancel out. That is, the data is all balanced, or zeroes out, precisely at the mean of 3. One consequence of the mean being the balancing point of the data is the mean is affected by extreme data values. To illustrate this, here we can look at some data that is balanced at the mean. But if the minimum data value was extremely small, that is, way far below all the rest of the other data values, the mean would have to compensate for this to keep everything in balance. Also, if the maximum data value was extremely large, that is, it deviated much farther than all the other data values, the mean would have to compensate for this much bigger data value to keep everything in balance. The mean must adjust for extreme data values to maintain the balance. Thus, the mean could produce distorted results whenever the data values include what statisticians call outliers. that is, extremely small or extremely large data values that deviate tremendously from the other population or sample values. So, as long as outliers are not present in the data, the mean is the preferred method for measuring central tendency.